here with the Fourier series representation of periodic signals. The properties that Fourier series has for the periodic signals. It turns out that Fourier transform exhibit similar properties, and that gives a great deal of insight into the Fourier transform representation of a very broad class of signals, which are usually, they don't have to be periodic. It could be aperiodic as well. Okay, so again, these properties, just like Fourier series, they help us to ease the analysis of the representation of signals in context of Fourier transforms or series. So the properties of continuous time Fourier transforms, as you recall, as the case was for the Fourier series representation of periodic signals, properties of Fourier transform provide us with a significant amount of insight into the transform and into the relationship between the time domain and the frequency domain description of the signal. Okay, so in addition, many of such properties are often useful in reducing the complexity of the evaluation of Fourier transforms or the inverse transforms. Okay, so one of the similarity, if you notice in the Fourier analysis and synthesis equations, is that both the in the Fourier series representation of periodic signals, you have the summation, and you're summing up the complex harmonically related exponentials with their corresponding Fourier coefficients as their weighting. So it's a linear combination of complex exponentials. So summation operation inherently is a linear or mathematical operator. Over here you have an integration, which is again a linear mathematical operation. So properties such as linearity is going to hold for both. Okay, so you will see that there is a very close connection with the properties that we have talked of earlier for Fourier series. Similar properties are going to be hold for Fourier transform representations of signals. So as introduced earlier, a signal xt and its Fourier transform xt omega are related by the Fourier transform synthesis and analysis equation. Okay, so for example, over here, xt is also being represented by complex exponentials having the weight of xj omega by 2 pi d omega. Okay, where omega is basically k omega naught. And if you recall the reasoning in the previous videos, we said this that as the time period becomes large, then the fundamental frequency omega naught for this 2 pi by t becomes small. So the harmonically related components k omega naught becomes very close, or they come just next to each other. So omega becomes a continuum. Okay, it becomes a continuous variable. Okay, so where x of j omega is defined as the integration of xt e j omega t. This is also known as the Fourier integral or the Fourier transform of xt, omega being the continuous variable. So what xj omega is? Well, xj omega itself is are the Fourier coefficients, right? They give you the sort of if you plot xj omega, the real and the phase parts of that, you'll see that how much contribution each Fourier coefficient is contributing into the signal. Okay, it's a representation of the magnitude of, for example, or the power of each Fourier coefficient that it is contributing into the signal xt. Okay, all right. So xt omega again is just like Fourier coefficients. Okay, which you can see over here as well. But in the Fourier synthesis equation, we have this weights of the exponential as xj omega divided by 2 pi into d omega. Okay. Okay. So as far as the notations are concerned, we'll sometimes find it convenient to refer xj omega with the notation of Fourier transform of xt, and xt with the notation of Fourier inverse of xj omega. Okay, so we're using f of xt to represent the Fourier of xt, and then Fourier inverse is inverse Fourier transform of xj omega. So we'll also refer to xt and xj omega as a Fourier transform pair notation. That is, xt is paired with xj omega through the Fourier relationships. Xj omega is the Fourier representation of xt, and the inverse Fourier transform is xt. Basically, it means that there's a one-to-one mapping between xt and xj omega, and this mapping is unique. So, okay, well, if you can go in the forward direction, you can take the inverse transform, and you can show that the reverse is indeed xt. Okay, there could not be any other signal other than xt. So this is a unique or one-to-one representation of the Fourier transform pair. As an example, for example, 1 over a plus j omega is a Fourier transform of a unilateral signal e minus at ut, okay, which exists for t greater than 0. So the Fourier transform of this signal is 1 over 1 plus 1 over a plus j omega. So the Fourier inverse of this relationship 1 over a plus j omega is e minus at ut. Okay, so this is just a as far as the notation is concerned. So e minus at ut has a Fourier relationship with, it's a Fourier pair with the Fourier pair of e minus at ut is 1 over a plus j omega. So so you can show that in the forward direction this is the Fourier transform, and in the reverse direction this is the inverse. Okay, so that's a one-to-one mapping between these two pairs. Okay, so now let's talk about the first linearity of Fourier transforms. So if xt has a Fourier transform of xt omega, similarly if yt has a Fourier, yt is another signal not equal to xt, has no relationship to xt whatsoever. If xt has a Fourier pair of xt omega, then yt is some other signal having Fourier pair of yj omega. If you make a linear combination of these two signals as axt plus byt, where a and b are arbitrary constants, then their Fourier pairs in terms of their transforms will be a xt omega plus b yj omega. I mean, this property is very it's basic. It can be shown by using the Fourier transform integral. Okay, I mean you can have any linear combination of signals. These are two signals. You can have any linear combination of more than two signals, three signals, four signals. Okay, this property is easily extended to a linear combination of an arbitrary number of signals. Okay, you see the idea behind this is that, okay, if you have this signal, let's call this z of t or whatever, it is a linear combination of xt and yt. So you have the signal axt plus byt. This is my so what I'm going to do is I'm going to write the Fourier integral for that, and this has to be multiplied by e to the minus j omega t to find the transform. And then you can see that since integration is a linear operation, we can bifurcate this integration into two integrations. Okay, so what we are going to have is a x of t into e minus j omega t. Then I have another integral similar to this one where it will be, okay, plus b y of t, then e minus j omega t. So you see these two integrations are the Fourier transforms of the signals xt and yt. Therefore, the result is a capital X of j omega plus b capital Y of j omega. Okay, so this property is very similar to that of Fourier series. Okay, in which if you have two periodic signals xt and yt, and you have to represent them in terms of Fourier series coefficients, Fourier series expansions, if you add them up, the Fourier coefficients are just the linear combination of the respective Fourier series coefficients of xt and yt. Similarly over here, the Fourier transform representation of the resulting signal, which is a linear combination of xt and yt, axt plus byt, then the Fourier transform representation in a very similar manner to Fourier series is a linear combination of the transforms of respective signals. Okay, so this is ax j omega plus by j omega, and there is no reason, I mean, you can go on expanding this linear combination, so it could be plus, for example, plus c z of t, and there will be plus c z of j omega. Okay, so the integration it can trifurcate, or it can, it's a linear operation, so you can have as many linear integrations, okay, separate integrations, and those are transforms like this over here. For example, this is x j omega, this is y j omega. Okay, so again, any signal that is a linear combination of signals, of any arbitrary signals, then the response or the Fourier transform representation will be the linear combination of each Fourier transform of each respective signal. Okay, so that's linearity. Then comes the time shift. So what it means is that, okay, now if you have the Fourier transform pair xt with xj omega, then if there's a time shift, any arbitrary time shift t naught can be positive or a negative quantity. If x is the signal is shifted in time, then that means in frequency domain there's a multiplication with exponential, and this exponential implies that there is no change in the magnitude of the Fourier transform. I mean, similar to Fourier series, if you recall, the Fourier coefficients were not being affected, right? I mean, look, if the waveform is simply, if, for example, you have a certain waveform of xt, and you simply shift it by, let's say, t equal to t naught. Okay, so your origin is starting from somewhere, let's say t naught. I think I've not reproduced the exact waveform, but anyways, the idea is that if this second graph refers to xt minus t naught, represent xt minus t naught, the Fourier coefficients or the frequency components that constitute the signal, they're not altered. Okay, they stay the same, but it's just the multiplication of ej omega t naught, which refers to the addition of phase in the transform domain, shows up. I mean, an addition of phase shows up in the transform domain. Other than that, since the waveform is not altered, it's simply shifted or delayed in time or advanced in time, the Fourier coefficients, the Fourier or the frequency components, they're not altered. Okay, I mean, the magnitude response is going to stay the same. You see, the magnitude response, if you take the magnitude of both sides, it is still x of j omega, right? I mean, the magnitude stays the same. It's invariant. It's invariant under the transformation. That signal is delayed or advanced in time. The magnitude response stays the same. However, you will see that the phase, as a consequence of delaying the signal, the pair will be as such. Okay, let me write this as pair xt minus t naught. The Fourier transform pair will be, there will be a shift in the phase quantity. So it will be j omega minus omega t naught, right? This is the phase that is this exponential is contributing. The phase is minus omega t naught, so which is going to be added in the phase response. Okay. Other than that, the magnitude stays the same. That which means the strengths of the harmonics, which is constituting the signal, there's no difference. They're going to stay the same. Okay, the power is going to stay the same. So just to establish or show the property, let's consider the inverse Fourier transform equation. So given x of j omega, you can take the inverse Fourier transform to show that this is xt. So if you replace t by t minus t naught in this equation, on the left hand side we obtain xt minus t naught, and then you have to replace t over here as well. This becomes et minus t naught. Then you can just group this inside this together with xj omega. So you have two exponentials, ej omega t and then e minus j omega t naught over here. And if you see this expression becomes the Fourier pair of xt minus t naught. Okay, this expression, I mean, you are taking the inverse Fourier transform of not x of j omega but e of minus j omega t naught x j omega, and multiplying with e j omega t and then taking the Fourier transform. So this becomes the inverse. So you're taking the inverse of this function, e minus j omega t naught x j omega. That simply implies, well, the implication is that x of t minus t naught is the inverse Fourier transform. Is the inverse Fourier transform of e minus j omega t naught x j omega. That's how you look at this integration. It's the inverse Fourier transform of x j omega e minus j omega t naught. Okay. Again, it just simply refers to the addition of phase of minus omega t naught to the phase of x j omega, while the magnitude stays the same. Okay, so recognize the synthesis equation for xt minus t naught. We conclude that xt minus t naught has a Fourier transform pair with e minus j omega t naught x j omega. So one consequence of the time shift property is that a signal which is shifted in a time does not have the magnitude of its Fourier transform altered. Okay, so there is no change in the magnitude response. That is if we express xj omega in polar form. Okay, so you see the Fourier transform of xt is xj omega, which can be expressed in terms of magnitude and a phase response. Then we know that the Fourier transform pair of xt minus t naught is e minus j omega t naught xj omega. So there's just a change in the phase. That's it. So thus the effect of time shift on a signal is to introduce into its transform a phase shift, which is namely minus omega t naught, and again it's a linear function of omega. Okay. Now to bring these two properties into use, let's see this example 4.9 from the course text. So to illustrate the usefulness of the Fourier transform properties that we have discussed, linearity and time shift, let us consider the evaluation of Fourier transform of the signal xt shown in figure 15a. Okay, this is for figure 15a. It shows the signal xt over here, right? And well, it's not very hard to see that it consists of it can be decomposed into two rectangular pulses that we've already considered. I mean, we know what the Fourier transform is for x1 and x2t. So for example, if you try to decompose xt into x1 and x2, you can say this. Okay, for example, the origin is simply shifted for x1t to let's say 2.5 over here. Okay, so if I can write this this shift as x1, well, these two signals are shifted and they are combined somehow. So let's see if we can work this relationship out. So if we can decompose this, so decomposing the signal into a linear combination of two simpler signals. So we have two simpler signals x1 and x2, and we have signal xt, for example 4.9. B and C are the two components of the signals used to represent xt. Okay, so okay, and the first signal let's say is shifted by 2.5. Then what about the next one? Well, the next one is also shifted by the same amount. Okay, I mean, if I shift this origin to 2.5, then I have to add this. So this will be x2 of t minus 2.5. So let's see if we have this thing. You see, writing the expression means that okay, on the time axis, if this is 2.5, then the first signal was my x1t, right? And it will have the limits up until, well, it's from minus 0.5 to 0.5. So there will be 2 over here, and then there will be 3 over here. So this is my x1. That's the first part, x1t minus 2.5. The second part is x2t, and if it is shifted at 2.5, then 1.5. I have to add 1.5 to 2.5, right? I mean, if I'm also going to shift that, so then it will be 4, and then minus 1.5 plus 2.5 is 1, which is the case on this time scale as well. So okay, then it's also a unity magnitude. So probably I have 1. Since they both are going to add up, it's going to be 2, right? But this is 1.5, so I have to multiply this, the first signal, with half. Okay, to make the magnitude as 1.5, and the rest is 1. Okay, that's it. So this is my decomposition. Now, what is the Fourier transform of xt? Well, to write the Fourier transform from linearity, if you recall, do we have the Fourier transform? I think if you recall example 4.4, we talked about that in previous videos. There was a rectangular pulse which was defined as such over an arbitrary time period, having magnitude of 1 over the time period when t is between minus t1 to plus t1 and 0 otherwise. So as shown in 4.8, we applied the Fourier transform integral and found out that xj omega is a sinc function. Okay, this is of this form. So we have the Fourier transform. This is the Fourier transform is a sinc function of a rectangular pulse. It has a main lobe width of 2 pi by t1 and the height of 2t1. So if we know this Fourier transform for rectangular pulse, then using the properties of linearity and time shift, well, we can write this as, so what's for example x1, okay, x1 of t, let's write the Fourier transform separately. It has the Fourier transform of, let me use this to, it's 2 sine omega t1 by omega. So what is t1? 2 sine omega, 2 sine of omega t1. Well, instead of t1 I can put this 1 over 2 over here. Okay, so this is simply omega by 2 divided by omega. Okay, again a sinc function. So this is again, this is t1 is 1 by 2, so I just replace t1 as 1 by 2. Okay, so it becomes twice sine omega by 2 over omega. Similarly, x2t, the only difference is only the width of the signal. Okay, so the difference in the time of this pulse, existence of the pulse. So this becomes x2t is twice sine of 3 omega by 2, because t1 is 3 by 2 divided by omega. So these are my two transforms, which I know previously we evaluated the transform for the rectangular pulse. The only difference is the time is different. The t1s are different. The time period over which the pulse is existing, okay, it's different. So we can write the transform as such. Okay, now since we have the two Fourier transform pairs, we can write the Fourier transform pair for xt as using the linearity property and the time shift. Well, for x1t, there is going to be an exponential multiplication that will be, since this is shifted by 2.5, so it will be minus j omega, or I can write this as 5 omega by 2. Then there is a factor of half, which simply gets multiplied by this 2, so this vanishes. Then you will have sine of omega by 2 by omega. Okay, so this is my first that's the first transform for x1t. For x2t, we have the same shift. Okay, so perhaps you can take this out of the expression, and we are left with by linearity, you just have to add the Fourier transform of the second signal, which is again shifted, so the exponential is common to both. Shift is the same, 2.5. So in the phase of the signal, I mean the phase of xt, we'll have minus 5 by 2 omega, which is a linear function of frequency. It's just going to add the phase, but the magnitude response stays the same. The there's no alteration in the magnitude response. Well, there is alteration because we decompose the signal xt into the two signals x1 and x2t, right? So if there was no phase shift, I mean if 2.5 was to be shifted at the origin, I mean if it would have looked something like this instead. So then there would have been no at the origin, if it would have stayed at the origin, since there was no time shift, we only would have used linearity. Then this expression won't have come into the transform. Okay, there wouldn't have been any phase shift or addition in the phase response. Then just this expression was good enough, right? But since the whole thing, whole waveform has shifted to 2.5 from the origin, right? So we have to consider this separately for two signals, since we bifurcated xt into two signals, decomposed it. So that's the difference. Okay. Okay. So that's how we, and that's this example showed the utility of these two properties, linearity and time shift. Okay. Okay. So actually we have observed this from figure 415. So we observed that xt can be expressed as a linear combination of two signals. These are rectangular pulses, and that was shown in 415b and c, or in this figure. This b and c are showing x1 and x2. These are the rectangular pulses. We know what is their Fourier transform. We evaluated in example 4.4. So we just plug this. We use this respective transforms with linearity and time shift property to derive the Fourier transform of the resulting signal. Okay, xt. All right. let's go ahead and discuss another useful property, that is the conjugation and conjugate symmetry. And this is the property that we will be dealing with more often than the other properties, because you see, if xt is a real signal, the Fourier transform you will see as a conjugate symmetric. That means you don't need to go ahead and show the transform for both the sides. I mean, the transform for omega greater than 0 is good enough. Okay, if you know what is the transform on one side of the vertical axis, you know what is the Fourier transform on the other side, because there is a conjugate symmetry. So it's a quite useful property again. So the conjugation property states that if xt has a Fourier pair of xj omega, if this is the Fourier pair, then x star of t, if you take the conjugate, it has a Fourier transform pair of x star of minus j omega. To show this, the property follows from the evaluation of the complex conjugate Fourier integral. That is, if you take the star of both sides, you can take this conjugation operation inside the integrand, so it becomes x star t ej omega t, because this is e minus j omega t, so it's a complex quantity, it becomes positive. Then replacing omega by minus omega, if you do this little mathematical artifice, you will see that this is x star of minus j omega on the left hand side. On the right hand side, this can be written as minus j minus omega, okay, because there was a plus over here. So just to write this, just maintain this plus, we can have this. If you're putting minus omega, then this has to be minus as well. So you have, because there's a plus over here. So what is this? Well, you see, this is the Fourier transform of basically this is the Fourier transform of not xt but x star of t. Okay, so this is the Fourier transform of x star t, which is the case we have shown over here as well. So these two quantities are Fourier transform pairs. Okay, so x star of minus j omega is the Fourier transform of x star t. So recognizing that the right hand side of the above equation is the Fourier transform analysis equation for x star t, the conjugation properties allow us to show that if now if xt is real, well, now comes the real deal, that if xt is real, okay, then xj omega has a conjugate symmetry. That is, if you, okay, in this step we maintained the star. We thought that xt is any general signal, it could be complex, so x star stayed there. But if xt is real, well, if xt is real, and that simply means if you take the star inside the integrand, then x star t and xt is the same thing, because xt is real, right? Xt is a real signal. And then you can write this as, this is plus, so you can write this as e minus j minus omega, which is the Fourier transform of xt, okay, but the Fourier transform will have omega replaced by minus omega. Therefore, x star j omega becomes x of minus j omega. This is the famous conjugate symmetry property of for real signal xt. That is, if you take, the Fourier transform of a real signal is symmetric, is conjugate symmetric. Okay. To understand this, let's take a unilateral signal xt, okay, which is existing for t greater than 0. It's an exponential signal. Now it has a Fourier transform of 1 over a plus j omega. If you take the conjugate of that, the quantity becomes 1 over a minus j omega, which is also x star of j omega. So these two quantities are the same. Okay, these two quantities are the same. So this follows from the conjugate symmetry property of real signals. You see, this is a real signal. Okay, so for real signal, there is a conjugate symmetry. That is, the conjugate of the Fourier transform is x of minus j omega. Okay. All right. So as one more consequence of conjugate symmetry, if we express xj omega in its rectangular form, that is, xj omega is it's a complex quantity, so it has both real parts and imaginary parts. Then if xt is real, then we have the conjugate symmetric property. This is the one that we talked of. Now, if you take x star of this equation, you take the conjugate, okay, then there is a negative sign with the imaginary quantity of Fourier transform. And if you replace omega by minus omega, then well, you have to do this for both the real part and the imaginary part, which is done over here. Now you see that from the conjugate property, the left hand side of the equations are equal. For the left hand side to be equal, the right hand side of these equations, of the above two equations, of these two equations, they should be equal. Which imply what? That the real part is symmetric. Okay, real part is an even function of omega, while the imaginary part is an odd function of omega. The imaginary part is an odd function of omega. Okay, so that gives some more insight into the, as a consequence of conjugate symmetry for real signals. The real part is an even function of omega, and it also implies that the imaginary part is an odd function in omega. And furthermore, you will see that the magnitude part becomes also. I mean, this is one way to express the complex quantity in terms of the rectangular form. You can also write this in a polar form, right? I mean, xj omega can be written in terms of magnitude and phase. You see this magnitude will become an even function in omega, while the phase is an odd function of omega. So that is the real part of Fourier transform is an even function of frequency, and the imaginary part is an odd function of frequency that we talked earlier. Similarly, if we express xj omega in a polar form as such, then it follows from the conjugate symmetry property that xj omega is an even function of omega, and the phase is an odd function of omega. Okay, so for real signals, as a consequence of conjugate symmetry, its magnitude is even while its phase is odd in omega. So thus, when computing or displaying the Fourier transform of real value signal, the real and imaginary parts of the magnitude and the phase of transform need only to be specified positive frequencies, as the values for the negative frequencies can be determined directly from the values of omega greater than 0. Using the relationships just derived as a further consequence of conjugate symmetry, if xt is both real and even. Now, so up until now we said that okay, xt is real. What if xt is both real and even? Well, it turns out if xt is both real and even as a consequence of conjugate symmetry property, that the Fourier transform is also conjugate. It's also conjugate symmetric. It's also real and it's also even. Then xj omega will be real and even. Okay. To see this, you see that if you replace just omega by minus omega on both sides of the Fourier integral, well, this is the expression, and then simply substituting tau is some dummy variable which is minus t. Okay, so the integration limits there, it's not a problem. You can add minus infinity plus infinity, and x of t is because it's a negative sign, so you can just reverse the order again, minus infinity plus infinity. So okay, when tau is minus t, then inside the argument of the signal it's minus tau, and you have to replace it over here as well. So this is t is equal to minus tau, so this is e minus j omega tau d tau, and this is your x of minus j omega. Now since x tau is x minus tau, this implies that xt is an even signal. If it is an even signal, then x of minus j omega, since this is even signal, x minus tau is x tau, right? And what is this? This is the Fourier transform of xt, xj omega, right? So xj omega and x of minus j omega are equal. That means that the Fourier transform is also real and even. Okay, it's also real and even. So xj omega is equal to, these two quantities are equal. Xj omega is x minus j omega. So thus xj omega is an even function. This together with the conjugate symmetric also requires that x star is xj omega. That is xj omega is real. So together with the symmetry property, if x minus j omega is equal to x of j omega, then you see this quantity and this quantity has to be equal, right? And this implies what? This implies xj omega is real. Xj omega is real. That is, the imaginary part of this quantity is 0. So for real and even signals, the imaginary part of Fourier transform is 0. So in a similar manner, it can be shown that if xt is real and odd function of time, that is xt is minus x of minus t, then xj omega is purely imaginary and odd. So since a real function xt can always be expressed in terms of sum of even functions and odd functions, you see any arbitrary function, if you recall in chapter 1 of Oppenheim and Schaeffer, we said that okay, xt can be decomposed into even and odd functions. Then from linearity, of the Fourier transform. The Fourier transform of Xt is the Fourier transform. Again, you can apply the linearity to show that the Fourier transform of Xt can be decomposed into two transforms. That's the even part of the signal and the odd part of the signal. And then from the preceding discussion, we said that the even part is the real function and the odd part is purely imaginary. Therefore, we conclude that Xt is real if Xt is the Fourier transform of Xj omega. The even part is the real Xj omega because Xj omega is the real quantity. The odd part is purely imaginary quantity, purely imaginary, so it's imaginary Xj omega. So this example shows, gives an insight into the usefulness of this property, conjugate symmetry. So let's consider again the Fourier transform evaluation of example 4.2. The same signal was Xt is equal to E minus A modulus of T, where A is greater than 0. Okay, so this is a bilateral signal which exists on both sides for some positive quantity of A. I mean, that's how the signal looks like. So this is E minus AT on the positive side. On the negative side, it looks like this. Okay, A is a positive quantity, so it has to decay on both sides. So this time we will utilize the symmetry property of the Fourier transform to aid in the evaluation process. So this is minus A magnitude of T. Okay. So all we know is, for example, in the very beginning from example 4.1 also, if you recall, you see Xt has a Fourier transform pair of 1 over A plus J omega. So note that for t greater than 0, Xt equals E minus AT ut, okay, and while for t less than 0, Xt takes the mirror image of the values. That is, this signal can be bifurcated into two functions. This is for t greater than 0. For t less than 0, this is E of AT u minus t, and well, you can also write this as 2 multiply and divide by 2 to make it look like an even function of E minus AT ut. Now we know that for an even signal, the Fourier transform, since E minus AT is real valued, the symmetry property of Fourier transform leads us to conclude that for an even signal, the Fourier transform is a real part of 1 over A plus J omega. Okay, so so the real part of this quantity is 2A over A squared plus omega squared. So that's the Fourier transform of E minus A modulus of T. That's the Fourier transform of the entire signal. So it follows from the conjugate symmetry property, and that if the signal is real and even, the Fourier transform is always it's first it's an even function of omega, then it's real. Okay, so you see over here, it also implies that x of j omega is first of all x star of j omega, so it's a real quantity. There's the conjugate, taking conjugate doesn't matters. Okay, and the other thing is that it's also even, that is j omega is x of minus j omega. Okay, so it's an even function. So for a real valued signal, the Fourier transform is conjugate symmetric. But for real and even signal, the Fourier transform is real and even. Okay, that's the point over here. If it was an odd function, if Xt was an odd function in t, then the Fourier transform would have been purely imaginary and odd function in omega. Okay, so that's it.